for global functions and PCPs.
Thank you very much, Noam, and thank you all for coming to this final talk. So in the previous two talks, we talked about what are unique games, what are two-to-one games, and how is analysis related to it. And we finished by stating this statement for the agreement for the soundness of the Grassmann test. And we showed only one direction, but we showed that this is true if and only if some expansion theorem holds for the Grassmann graph. So I was debating what to do in this talk, and eventually I decided that it would be good if I gave you some sense of why this expansion theorem is true. So I'm not going to give you the full proof. I don't have enough boards, but anyway, I'll give you some sense to why this is true, and then talk a little bit more generally about what is global hyperconductivity and what it is good for besides PCPs. So let's recall. So we denoted by GRR and the set of subspaces dimension in F2 to the n. And you should also think about it as denoting the Grassmann graph itself. Namely, we have also the set of edges which are between L and L prime if they intersect in dimension 1 less. So let's recall what was the expansion theorem. So we need a definition. So if I have a set of vertices, then it is called R epsilon global. So I also do random, so I'm going to use these two terms interchangeably. If whenever I take this small set that doesn't expand, that has dimension at most R, so for every subspace X and W inside F2 to the n, where the dimension of X is small and the codimension of W is small, it holds that S is not very dense inside out. Okay, so this is what we call a global set. And with this in mind, the expansion theorem of the Grassmann graph says that for every greater than 0, there exists some R and delta such that if I have a small set which is global, then the expansion of S is close to 1. Well, let me remind you that the expansion of S is the probability that when I choose a random vertex from S, then to take a random edge, that I escape S. So now we are going to devote a chunk of time to get some sense to why this theorem is true. Of course, as I said, I'm not going to give you the full proof, but I hope that you will get some idea of why this is true. Okay. So the main benefit of working with such a statement about sets as opposed to a statement about some assignments is that, you know, a set is a Boolean function. So the first thing we are going to do is we're going to define a Boolean function, which is just the integrator of the set. And once we do that, we can start applying spectral tools to study the function. And this is what we're going to do. And you'll see here a bunch of things that were already mentioned in several other talks. For example, the first thing that I'm going to tell you is that there exists this degree decomposition, which is really the same as what Max discussed in his talk. So I'm not going to prove things too formally, but I hope that there will be some sense in it. For degree decomposition. So whenever you want to define some notion of degree, it's best to think of the simplest thing that you would like to call a degree D function, which is a junta, as Noam mentioned in his talks, and then take a span. And this will give you a nice notion of degree. So with this in mind, if we have, so if we look at a set X, a subspace that has dimension at most D, then we can look at the indicator function of containing S, and this will be referred to as a D junta. No, because it really depends on whether I contain some D vectors or not. So now to define degrees, I can just take a span of this. So if I want to define the space of degree at most D functions, this is going to be denoted by J at most D, and I'm going to define it to be the span of all of these indicators. So far, so good. Okay. So just as in Max's talk, this is not going to give me a nice orthogonal decomposition because, in J less than D, I have also degree D-1 functions, degree D-2 functions, and so on. And I want to sort of throw them away. So we do the same thing. We define a set of pure degree D functions to be degree at most D functions that are orthogonal degree at most D-1 functions. So throughout, I'm going to think of the inner product space, which is F times G, the expectation over L of L. So this is a function. So this is a function that takes the input L and outputs 1 if X is contained in L. So L is the input of the function. A fixed X, and now we define a function over subspaces. The function outputs 1 if and only if the subspace contains X. Okay. Any more questions? Yeah, so Noam justifiably said that these functions really correspond to one of the types of non-globalness that we have, which this X is. You could have justifiably said, okay, what about dictators like indicator of L contained in some hyperplane? So maybe not hyperplane, maybe something of codimension at most D. Exactly. It's an exercise to show that if W is a hyperplane of codimension 1, then you can write this as a sum of these things for X of dimension 1. So actually, the two definitions are the same. But this kind of duality is, this is the first sign that complicated things could happen, because you have to choose a basis, one of them, but then somehow your argument is going to take care of both of them together, because this is a statement that is concerned with both of them. But anyway, I'm getting ahead of myself, but thank you now for this question. Okay. Cool. So we have all of these spaces out of the way, and then you can just say that all of your real valued function on the Grassmann graph are the result of the direct sum of these spaces. Okay. In other words, if I have my function f, which is the indicator, so maybe let's call this. We only have one. So if we look at our function f from the beginning, then we can just decompose it according to this decomposition. So you can say a lot of things about these spaces. You can compute their dimensions, but we don't want to do any of that. All that we're going to care about is that when you look at the adjacency matrix of the Grassmann graph, then these spaces are actually eigenspaces. So this is a fact. So let T be the normalized adjacency matrix of the graph. So here's the fact. With I 0, 12. I'm slightly cheating, but never mind. Space A equals I is an eigenspace of T with eigenvalue. Minus I plus maybe something small. Okay. So I just want to say it because I don't want to completely cheat. So you may say that you may observe that this is false because the trace of T is 0. And these are positive numbers. So how can it be? So the point is that for I, which is equal to L, this is not actually correct, but the eigenvalue is very small. That we don't. It's a negative small number that we don't care about. But with this out of the way, let's pretend that this is true. Okay. So now we have our function f, we have our decomposition, and we know something about the eigenvalues. So now we're just going to express expansion in terms of this decomposition and see what we get. So if you look at 1 minus the expansion of S, then you can, this is the fraction of edges that stay inside the set S. So you can write it as 1 over the measure of S times the inner product between F and the adjacency operator applied on F. Because this counts the number of edges that are inside S once you start with something inside S. So now we plug in this decomposition and we use the eigenvalues and get, so I'm going to ignore this little of 1. We get that this is equal to 1 over mu S times summation from I equals 0 to L 2 to the minus I times the L2 norm of Fi. Right here, we use the fact that Fi and Fj are orthogonal. We used this fact above, and we got a nice spectral expression for our expansion. Okay. So this by itself is not going to buy you much, but you can already see something which is non-trivial, which is going to motivate somewhat this theorem. So here is a statement which is very simple. So we want to prove that pseudo-random sets have close to one expansion. And the weakest form of pseudo-randomness that you can think about is just the set being small, like nothing about this X and W. So here's what smallness buys you. Okay. Suppose mu of S isn't most delta. Then the expansion of S has to be at least somewhat large. At least half minus a little bit. Okay, so let's prove it. Okay, can anybody tell me the proof? Not now.
Fact that F0 is constant, like the constant part, and then cut it off with the eigenvalue half.
Yeah, exactly. So we're going to use star. So star. So as Max said, we're going to separate out I equals 0 because there the eigenvalue is not so good. It's just 1. And we're going to use the fact that we actually know what F0 is. F0 is a constant function. It is the constant function which is closest to F, and namely just its average. So by star, okay, let's do it slowly. This is F0 norm plus summation I from 1 to L to the minus I times the 2 norm of Fi squared. So as we said, this is the measure. So 1 over mu S. So as we said, F0 is just the measure of S. So its 2 norm is the measure of S squared. So we get mu of S from the first guy. And what about the other thing? Well, each one of these eigenvalues is at most half. This is all I'm going to use. So plus 1 over 2 mu of S times summation I from 1 to L, the 2 norm of Fi squared. And now we're going to use Parseval. So we know that the sum of all of the 2 norms of Fi is the 2 norm of F. Therefore, this incomplete sum is equal to the 2 norm of F squared minus the 2 norm of F0 squared, which is just mu of S minus mu of S squared. So we plug it in, we simplify, and we get that this is equal to, let's see, half plus mu of S over 2. So now you rearrange it and you get the claim. So this is very simple. We didn't really do anything, but at least writing down this line, this suggests how we are going to get beyond half. So the reason that we got this half expansion is because below eigenvalue half, there is only one function, and we know what to say about the component there. So if we could say something interesting about not only F0, but also F1, then it stands to reason that we are going to push beyond this quarter, this half, and the higher we go in the degrees, the better this is going to get. So in other words, if we knew that when you look at Fi, the two norm of it is at most some small epsilon times the measure of S, then you can sort of repeat this argument, truncate everything below, so for every I less than D, R. Then you can repeat this argument, everything below R we take together. You know that the mass there is small just because of this. Everything above it, well, you're going to use stronger bound on the eigenvalue. It's going to be 2 to the minus R plus 1, and it's going to improve. If you check out the math, this is what you would get. You would get that the expansion is very close to 1, as long as R is sufficiently large and epsilon is small. So now we look at this thing, and this is really the same as the level D or level I inequality that Noam mentioned. And if we had this level D inequality in this case, then we'd be done. But then we'd also not use globalness. So this has to fail. So now the question is, when can we say that we only have low mass on the low levels? In other words, this theorem reduces to the following equivalent result. For every epsilon greater than 0, there exists some R and delta. For epsilon greater than 0, there exists delta such that if S is R delta global, then for the integer of it, we have that the mass on level at most I, most epsilon times the measure of S for all I less than R. Okay, so I hope that it is clear that in order to prove the expansion theorem, now it suffices to prove this type of level D inequality, which is that if you're global, then indeed your mass on the low levels is small. And I'm not, as I said, I'm not going to prove it, but I'm going to give you some sense to why this is true in the simplest case that still gives some idea, which is the case that R equals 1. This is the simplest case, but it's still far from trivial. So let's look at F1. So the first thing that we need is actually some nice formula for it. And this formula is going to look very much like the formula that Max was suggesting, which is you take some function of the points and then you apply the up operator on it. So this is really what's going to happen. So it turns out that there exists a function little f equals to 1 that assigns to each point some real number, such that to evaluate capital F of L, what you do is you sum over all of the points inside L, and you take the value of little f of x. So this is a formula. And actually there is one important additional feature of it, which is actually, I can actually tell you what this little f is. So little f of 1 of x. So I'm slightly cheating with the normalization, but forgive me. So little f of 1 of x is the difference in measures in the set S when you look at its measure overall and its measure when you restrict yourself to containing x. So this notation means the probability that L is inside S, condition on x being in L. So this is somewhat of a good sign because at least somewhere in the picture there is the density of S inside this so-called zoom-ins. So it seems like we're going in the right direction, but we're still not there. So we want to prove this theorem, so let's assume that it's false. Let's assume that we have a lot of mass on F1. What if so what if this happens? Well, this means that you have this degree 1 function, and it is correlated with a Boolean function. So you can observe that the two norm of F1 is the same as the inner product between F and F1. This is just orthogonality. So you have a degree 1 function, which is correlated with a Boolean function. So let's push things to the extreme. We're already at level 1. So let's say that somehow magically F1 itself is Boolean valued. Because this sort of thing suggest if you are correlated to Boolean function, it sort of suggests that you have some Boolean behavior. So let's push it to the extreme. So how could this sum be a Boolean function? So let's think about it. So now we're going to think of things as random variables. So let's suppose that we choose a subspace L randomly, and then we look at the points in it. Then this F1 of L is kind of a sum of random variables. And to me, these random variables seem independent. Right? It's a bunch of points in subspace. Why not? And we know that if you have a sum of independent random variables, then it's not going to be Boolean. It's going to be some Gaussian-looking thing. But we know that it is not Gaussian-looking thing. So how could it be the case? Well, there are two options. So maybe this is like sum of Bernoulli random variables where the parameter of the Bernoulli is very small. And then this is going to be Poisson-like random variable, and then maybe it's Boolean. But in order for there to be a Poisson type behavior, it means that most of these little f1s of x have to be 0, and the rest have to be very large. And when I say a few, so you can check out the numbers because L contains 2 to the L points. A few here is like something of the order of 2 to the n minus L. So I'm being very informal. I'm not going to go into any more formalities than that. But I claim that in this option we're done. So why is that? Well, we have a formula for f1 of x. And we got that the difference between this measure and this measure is large. In particular, it means that the measure inside the link of X is larger. And we're not pseudo-random. Okay. So this is option one, and it seems like, okay, sounds feasible, but then you don't see these hyperplanes anywhere. So there must be another option. So recall that I said that F1 is a sum of independent looking things, and I sort of said it quickly so that no one asks me about it. And the reason is that, okay, maybe they're not independent. So, you know, a subspace is not an arbitrary set, it has a structure. So clearly, if we have 3 points in a subspace, then for free, we're going to get an additional point. We're going to get that X plus Y. But Z is also in there. So this says that there are possible correlations, like 4-wise correlations in here. So option 2. One of X are correlated. And if you do this carefully, what you actually get is that they have this correlation in 4 points. And when you normalize correctly, what you're going to get is that 2 to the 3L times the expectation over XYZ, the product of 4 values. Is a constant. Yeah, so this is true, but so really when you do this thing as you should do it, then the way you formalize this Boolean-like behavior is using a relation between the 4 norm of F1 and the 2 norm of F1, just in like any whole hyper-contractivity inequality. And you know, even norms are nicer because you don't have to put absolute values. So this is why you're going to get 4-wise correlations. Maybe you can get 3-wise correlations, but I don't know how to work with odd moments with absolute value, which kills me. So yeah, but this is the only reason. Okay. So this is the second option. Now you have this very nice looking term that if you have done any Fourier analysis in your life, then this screams expand me according to the Fourier basis. So now we think of f1 of x as a function for f2 to the n. Two is, and you expand it according to the Fourier basis in f2 to the n. So you expand it and you get it equals 1 of x is equal to summation over s. Some Fourier coefficients. Ks of x. You plug it in and you get something very nice. You get that, maybe let's do it here. So when you do this calculation, like you plug in the Fourier expansion of f and do expectation, you're going to get it to the 3L times sum of Fourier coefficients to the fourth. It is a constant. And once you do the standard stuff, you know, pull 2 squares out and handle with the rest by Parseval, you're going to get that there is one significant Fourier coefficient, at least one. But you have a very nice formula for f1, so you can figure out what the Fourier coefficients of it are. And when you do it, you're going to get that there exists some hyperplane. Well, S is significantly denser. Okay. So this is really, roughly speaking, the proof for the degree 1 case. And if you sit down to do it precisely, it's not even that hard. But you can imagine that once you go up in the degrees, it's going to get complicated. And it isn't all complicated, but it's not the end of the world. But this is really the way that the proof of the expansion theorem goes, at least ideally.
Sorry, why it's close to Boolean, or what's the intuition?
Yeah. So we're assuming that this theorem fails.
Yeah.
Therefore, we have a lot of mass on the first level. So what is the first level mass? It's the correlation between F1 and F itself. So this assumption really says that F1 is correlated with a Boolean function. So for simplicity, we said we replace the word correlated with Boolean behavior. But it's not really a big issue. Like once you transfer everything to 4 formats, you don't see the difference. This is just for intuition.
Yeah. Why there is three like also one object?
So you have to do the formal proof, but this is the only 2 cases for degree 1. It stands to reason that, if you have a sum of things, the only way that it's not Gaussian is if there are a few ones and most of them are 0, or there is dependency. Right, Sundrum theorem tells you that if things are independent and not too large in magnitude, it's going to be Gaussian. So this is kind of why you have 2 options.
And with the cross terms.
Sorry?
The cross terms, do you just get rid of
Which options?
like next time?
This?
Yeah.
So this is actually, here I didn't lie actually. So when you plug this Fourier expansion, you're going to get 4 Fourier coefficients, but to have non-zero contribution, they all have to be the same.
It's like so
Yeah.
it's like convolution. So PSG.
Here's one. And here's another one. Yeah.
What's the intuition for why this implies the hyperplane? There exists as a hyperplane?
So there is this duality between zoom in and zoom out. So once you have a function that measures how dense you get in points, it stands to reason that Fourier coefficients, which are dual, is going to measure closeness in like a increase in what is dual to points, which are hyperplanes. You can just actually compute it. It's not that hard. Any more questions?
You can also think of that condition as sort of for the additive energy of F1.
This one?
Yeah.
Um,
You can also just use this like using Bowell's energy balance theorem and random type results to get the subspace.
issue is that little f is not. I mean, it's not a set. It's a real value function.
Yeah.
So what do you mean by?
So that's just the expression for additive energy.
Right.
So all these results say if you have a function with high additive energy, then it has a correlation with the subspace.
Yeah, this is exactly what we do. Right?
Yeah, I'm just saying that these are also, there are known classical results. I was wondering with that viewpoint, maybe
It's like one line computation. Why would you invoke a paper?
the subspace.
Yeah, it's only one line.
I agree that it's well known. I didn't say that this is anything special, but you don't need. So usually when you use this Balog summary stuff, it's for hard things. This is very simple. So As well said, it's a one-line commutation. Nothing wrong. Okay, cool. So I hope that I convinced you why this theorem is true for I equals 1, and you sort of get a sense that it should be true for general. So this finishes the story for the Grassmann graph. This was, motivated by PCP, but then you can take a step back and ask yourself, okay, we saw this expansion theorems and blah, blah. It was very hacky. We got some expansion results. We used it for PCP, but is this expansion type theorems more general, or is it, something very specific to Grassmann and you cannot do anything else with it? And it turns out that it's actually quite general phenomenon. So we already saw a few examples in this bootcamp about such places, and I'm going to mention them again, and maybe a few more. So following this Grassmann stuff, the first thing that we looked at together with Kivash, Noam Lifitz, and Owen Long is the simplest possible case you can think of, which is the p-bias cube. So I'm going to write product spaces. I want to avoid some annoying technicalities, so I'm really going to just think of about the p-bias cube, but everything that I'm going to say generalizes. So let's think of 0, 1 to them with the p-bias measure of p is small. So we already defined a graph over this vertex set, which is the noisy graph. So let me say it again. So let noisy cube, which I mean that given a vertex X, we're going to sample a neighbor by keeping each coordinate with probability half, otherwise resampling it according to Newton. This is for each I independently. Okay. So you can look at this graph and you can observe that this is also not a small cell expander. That's because of the same reasons. So you can look at the surface, which is all of the points X. So let's say X17 is equal to 1. And you have the measure of S. But then the expansion of S. Maybe plus little. Okay, so it's not a small set expander. So again, you can ask, are these the only type of sets that do not expand well? And yeah, this is true. So theorem, for that I need definition. So S is called epsilon global. If for every t, for every I, and then of size response d, if I look at the measure of S when I fix xi to be 1, I get at most epsilon. So this is the exact analog of what being global is for the p by s cube. Now we have a theorem that says if your set is sufficiently global, then the expansion is close to 1. Okay, so this is really the analog of what is happening on the Grassmann graph. And the proof of this is, much simpler. Like I'm not going to discuss it at all, but because we're working with a simpler space, you can be more greedy and ask, okay, this is small cell expansion. Can you get something that looks really like hyperconductivity? And the answer is yes. So, so first of all, you can prove a statement about real valued functions. So if you have a function, real value, global, so here I need to define a different notion of globality. So earlier we said something about the measure of S not being too large inside some domain. Here this is going to be the same, except that measure is going to be replaced by 2 norm. So by this I mean that expectation of fx squared condition on xi equals 1 is most epsilon for every I of size most r. And f is low degree. Then you can prove something that resembles hyperconductivity. So in hyperconductivity, you would be able to compare the 4 norm of f and the 2 norm of f, but here we're not quite able to do that. We get 2 norm of f to the half times this pseudo randomness, this globalness parameter. I think it's and the usual exponential in the degree. Okay, so this already gives you something which really looks like Bonami's lemma or hyperconductivity for real. And you can actually go further. You can give a statement that doesn't talk about globality at all, but give some weighted average of what happens when you do these restrictions. So I don't want to do it. It's just a formula which is going to look complicated, but this exists.
So what does that say? 2 norm of f to the power of what?
Sorry?
What is the exponent on the 2 norm?
Epsilon to the half, f2 to the half. So like in hyperconductivity, you would expect like the 2 norm of f here. But here you have to replace one of these norms by this 2 norms parameter.
What's the exponent on the 2 norm of f?
Sorry, on the 2?
The 2 norm of f?
Half.
Half.
Yeah.
Geometric.
Yeah. The geometric mean of globalness parameter and the 2. Sorry? I think this is tight, right? Yeah. Yeah. Okay. So we have the Grassman graph. Now we have the p-bias cube. And now you can again look at more complicated situations. And I'm not going to define anything, but I'm going to tell you that there are analogs of it for stuff like the Johnson graph, which is not a product space, but it kind of looks like a product space. So things still work out.
So the proof of this theorem, can you this theorem, you just prove it by, I mean, using small set expansion to get hyper-contractivity, and then like yeah, and then the noise operator applied to F kind of maintains this global property. So like is it the case that every object you encounter in the proof is global, and so you can assume it like that you're acting on a small set expansion?
No, so the proof of this actually mimics the usual proof of hyperconductivity very much. So there are several proofs of this. One of them is you can write a different statements for this, which generalizes, and then you can do induction. Another thing you can do is actually reduce this statement to some statement in the Boolean cube by using something like the replacement method. So the unbiased cube. So you can expand your function according to the p-biased basis. You can look at the form, then you can slowly replace these p-biased characters by unbiased characters, and you see what you get. And if you do it correctly, this is what you get. But it's not
not prove this directly, prove some other formula which is more explicit.
Yeah.
Than just
So in other words, you cannot go from the preceding theorem to this theorem.
no, yeah, it's the other way around. Yeah, you can also prove it directly. Like there are many proofs.
You want to explain what the Johnson graph is?
No, I don't have time for that.
It's the down up walk on the complete the complete complex.
Here you go. So there is also the symmetric group. There's an expansion for that, Max.
Down up walk on the complex. Yeah. And now the complex is a symmetric group.
Yeah, and in general, there is this quote about HDX that we already heard about by Max that also gets some stuff like that for high-dimensional expanders. So I don't want to define it because I don't have. I have 5 minutes and I want to say something more. Anyway, so there are a few other cases in which it's known, but for me, what is more interesting is that each one of these instances gives you some nice application. So, proving this sort of stuff for fun is good, but it's nice to know that it's good for something. So what is it good for? So we already saw that it's good for PCPs. So more specifically in this series of talks, we saw that it's good for unigames related stuff, but there are a few more connections that I'm not going to mention. There is some extension of unigames which is called reach to one games, where this is also useful. And I believe there will be a few more applications to PCP, but it's too early to tell. Secondly, this is the reason that we look at the p-bias cube. To start with, you have applications to sharp thresholds. So, if you have a function with the p-bias cube, which is monotone, you can start asking how quickly does it average jump when I increase p. So for most functions, it's going to increase very quickly. And you would like to say, if it doesn't increase quickly, then it's because I have some structure. And we can prove such theorems, and this uses this type of hyper-contractive inequalities. So thirdly, and this is the thing what Naomi is going to discuss a little bit in his talk, which is coming up next, is you can use it for external combinatorics. So you're going to talk about product presets, right? So it turns out that you can prove a bunch of results in external combinatorics, which otherwise seem unapproachable, but because the external examples resemble this type of sets that don't expand, you have some chance that this sort of machinery will help, and it's obvious to be the case that this is true many times. So fourth, it is also useful in some other protein codes. And testing the mother code. So I don't have enough time, so I'm not going to tell you what the problem is exactly, but maybe I am. So the problem is as follows. I have a function for f to the n to f2, and I know that locally it looks like a degree function. Namely, if I look at the subspace of dimension b plus 1, then the degree of the restriction of f must be close to 1 probability. Does this mean that f itself has to be close to degree d? Well, the answer turns out to be yes, and if you want to prove it and get nice bounds, this sort of tools are also useful. So these are just 4 types of problems where these sort of tools come in handy, and I believe there will be more areas. And this is part of the motivation for me to present to you this, like to look for other connections between global hyperconductivity and other areas, like maybe solution theory, as Noam suggested already, or things that we didn't think about at all. So that's it. Thank you. Are there any questions for those?
In there, the lower bound is some delta instead of epsilon. Can you say anything?
So you need half plus epsilon, no? Right, because any function has this probability at least half, and this is the inverse Gauss problem. Maybe. So we don't know how to apply this sort of tool to the inverse Gauss problem. This is something that there is a chance that it would work, but it needs to be very nice, but we don't know it.
It's also worth mentioning that this sharp fashion product improved the result of the game.
Yeah, so it didn't specify what the result is, but yeah, it builds on like many works, very sweet. Any more questions?
See you in 30 minutes.